From a scientific point of view, the concept of absolute nothingness is, by definition, a problematic and borderline notion. Science is built upon observing what exists, measuring it, and constructing explanatory models based on these observations. Within this methodological framework, a state that possesses no properties, no effects, and no measurable characteristics cannot become a direct subject of scientific investigation. This is because scientific knowledge always depends on some form of interaction. For this reason, absolute nothingness is not considered a conclusion reached by science, but rather an assumption that lies beyond its reach. In other words, science does not speak about absolute nothingness. Instead, it demonstrates that it cannot speak about it. In modern science, the concept of vacuum is often confused with the everyday understanding of nothingness. However, in physical terms, a vacuum is not a region where absolutely nothing exists. Even in what we call empty space, there are energy fluctuations, fields, particle-antiparticle pairs, and potential effects. This shows that, from a scientific standpoint, even the lowest density states of existence do not correspond to absolute nothingness. When science refers to a vacuum, it is still describing a physical state with specific properties. Thus, science does not investigate nothingness itself, but rather the boundary conditions and minimal forms of existence. Research at the quantum level has revealed that even in regions thought to be nothing, there are measurable effects. Virtual particles, energy fluctuations, and field oscillations suggest that even empty space has a dynamic structure. These findings make the idea of absolute nothingness even more controversial. However, it is important to note that science does not declare with certainty that absolute nothingness does not exist. Science merely states that, within the domains it can observe, no absolute nothingness has been encountered. This is the result of a methodological limitation, not an ontological claim. In other words, science is not saying nothingness does not exist, but rather there is no nothingness that can be observed by my methods. By definition, the scientific method works with testable, measurable, and repeatable propositions. For a hypothesis to be scientifically valid, it must, in principle, be falsifiable. Absolute nothingness, however, cannot be tested because testing requires interaction. In a situation where no interaction is assumed to exist, measuring instruments, observers, and experimental setups become meaningless. Therefore, science can neither confirm nor refute absolute nothingness. This is not a weakness of science. On the contrary, it is its strength. By acknowledging its own limits, science preserves its reliability. In scientific models concerning the origin of the universe, claims of absolute nothingness are deliberately avoided. Theories such as the Big Bang describe a beginning point, but they do not portray this beginning as absolute nothingness. Instead, the beginning is usually described as a state of extremely high density, a process in which physical laws operate in unfamiliar ways, or a mathematical boundary. This approach intentionally leaves the question, what was before, unanswered, because any definitive answer would go beyond current observational and modeling capacities. Thus, absolute nothingness remains outside the scope of scientific explanation. At this point, it becomes clear that scientific explanation, by its very nature, always starts with an assumption of existence. For measurement to occur, there must be something measurable. For observation to take place, there must be a phenomenon to observe. Therefore, science is fundamentally an existence-based discipline.